Hey folks, welcome back to another lesson, and we're now going to focus on the electromagnetic spectrum, which we've kind of touched upon when we did the space topic. And you may remember doing this activity in S3 when we got you to do the poster, and I remember you having to pick your favorite poster. So this is going to be fairly kind of focused, because it's more like revision really. So we're going to describe what the electromagnetic spectrum is, give examples of different parts of the EMS spectrum, including frequency, wavelength, and application. State the speed of electromagnetic waves and use this in calculations. So a wee bit of revision here from the previous lesson, and describe the energy of EM waves in relation to their frequency. So can you name the colours of the rainbow? So it's a nice wee starter. Hopefully you can do it. Pause the video while we go, and I'll show you the answer. So hopefully you managed to do that and you got the following, that it was red, orange, yellow, green, blue, indigo and violet. So we've got this Roy G. Biv, and you may remember that from last year as well. Now, what is a spectrum? A spectrum is a range of things that share similar properties. So I would like you to copy this down into your jotters as a wee note, because we're going to be talking about the electromagnetic spectrum. So light is an example of a spectrum, because you've just seen that, or we've just talked about there, that the light of a rainbow is all these different colours, and they all share similar properties. For example, they all have a wavelength, a frequency, and more importantly, they all travel at the same speed. It's part of the electromagnetic spectrum. So again, could you write that down? And a really important scientist, which you may have talked about in first year, is James Clerk Maxwell. And he was basically a Scottish scientist who discovered that light and all waves in the electromagnetic spectrum travel at 300 million meters per second, which you know already. So let's look at the electromagnetic spectrum. You've seen this diagram before, and you know that there are different parts of it with different names. And depending on which part it's in, it's got a different wavelength. As we go from radio waves to gamma rays, you can see the wavelength will steadily get smaller, and that they also have a frequency. And again, as you go from radio waves to gamma waves, the frequency of these increase, and we can only see a tiny part of the spectrum called the visible spectrum, okay, which is this wee bit here. Now, I'm going to cut straight to the chase, because we want to just get ready for the exams, and you have done this before in S3. This is what you need to know from the SQA. You have to know that all radiations in the electromagnetic spectrum are transverse waves, so that's a key word there, and they travel at the speed of light. And we're going to use these with satellite equations later on, or satellite questions later on. The second thing is you need to know the different bands of EM and compare the frequencies. Now, does that mean you have to remember or memorize all the frequencies? The answer is not really. As long as you know which part has a high and low frequency, you'll be okay. Give examples of sources, detectors, and applications of each band. So this is something that you need to go off, make your wee revision cards, or have some way to memorize these 3 bits of information. Okay. Now, to help you with this, this is probably the most important slide, okay? Because this slide contains all the information you need that the SQA expect you to basically remember. Now, I wouldn't bother remembering the exact wavelengths of these, or the frequencies. What I would remember though is the order of these parts of the electromagnetic spectrum. So I would expect you to be able to tell me the order is radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. And I would expect you to tell me that radio waves have the biggest wavelengths, and then they decrease up until you get to smallest wavelength in gamma rays. I would expect you to tell me that it's the opposite for frequency, that the frequency for radio waves are the smallest, and then they get bigger as you head towards the gamma rays. That is what I would expect to know for this diagram here. So make your own notes on that, okay, and make sure you are aware of the different parts of the EM spectrums, the size of the wavelength, and the size of the frequencies. The next bit you have to remember is this table here, and I'm afraid you do have to just memorize this. You need to remember the thing that can detect the part of the electromagnetic spectrum. So this is the part of the electromagnetic spectrum. This is, or rather, this is the source of the electromagnetic spectrum. So if you want to label this as the source, okay, you then have to remember the detector. Okay, so that's the thing that picks up the electromagnetic waves, and then you have to tell me an application. Okay, so copy this table into your jotter, make notes, sticky notes, etc. So radio transmitter gives out radio waves. They're picked up by aerials and they're used for communication. So, for example, you listen to the radio for maybe the traffic news or the weather report. A microwave oven, so let's use a microwave that you use to heat up foods. In this case, it's detected by a radar detector dish and it's used for heating food. An infrared heater is detected by a black bulb thermometer, and this is a tricky one. This is the main one that the SQA would accept, and it provides heat. A light bulb is detected by a light-dependent resistor, so there's a wee bit crossover with your electronics topic, and it provides light. The sun is part of your visible, your ultraviolet spectrum, sorry. Some fluorescent chemicals, and it helps body make vitamin D. X-ray machines, photofilm. If you've ever gone for an X-ray, you'll know that the doctor will show you your X-rays and it's like a photographic film. And they're used in airport scanners. Finally, nuclear reactor, you detect it with a GM counter, which we'll look at later on, and it can be used for sterilizing equipment. So make sure you know the information from this slide. Okay, now dangers of the electromagnetic spectrum. Well, as the frequency increases, the wavelengths get smaller. So that's quite a handy bit of thing to know. So I would write this down. Eventually, the waves are so small that they can interact with cells, DNA, and atoms, and this is called ionizing radiation. And we're going to have a look at this in more detail when we come to do the radiation topic. Okay, now because of that, we now have two parts of the electromagnetic spectrum, a non-ionizing part and an ionizing part. Okay, the ionizing radiation, as you're going to learn, is the really dangerous ones because those are the ones that can give you an increased chance of getting cancer. They're also the ones that are used to treat cancer. The non-ionizing radiation is relatively safe. So this is, for example, why we can have radios, because remember, there are millions of radio waves passing through each second, but it doesn't give you an increased risk of cancer. It doesn't boil you alive like it would a microwave. This is also why we can use mobile phone waves, because they use microwaves to communicate with each other. And of course, the visible spectrum, that's the one that you look at with your eyes, and we know that that's reasonably safe. Okay, so let's look at the energy of EM waves. Now, the first thing we have to remember is that as the frequency increases, the energy of the EM wave increases. Now, how does that work? Well, one way to imagine it, and I would do this with you in class if we were in class, is imagine you're bouncing a basketball, okay, or dribbling a basketball, okay? Now, if you think about it, every time the basketball hits off your hands, that's like a frequency, isn't it? Right? So you can measure the frequency of that basketball by counting how many times it hits your hand in 1 second. Now, think about what happens if we try to increase the amount of times that basketball starts hitting off your hand. So if we increase the frequency of that basketball bouncing, we're increasing the energy of it because it must have more kinetic energy to bounce faster, doesn't it? So we can think about waves the same way, because you think about it, waves also kind of oscillate or move backwards and forwards like our basketball, doesn't it? And the more it moves backwards and forwards, the greater its frequency, so therefore the greater its energy. So that's one way to remember how, as the frequency increases, the energy of the EM wave increases as well. Now, Wi-Fi uses a frequency of 2.4 gigahertz to 5 gigahertz. Now, giga, remember, is times 10 to the 9. So does that mean we're getting a large dose of radiation? Okay, And the answer to that is I'll tell you if you are doing higher physics, because we need a little bit more physics before we can actually explain that properly. Okay, the final part of our lesson now is a wee bit bitty, as we're going to look at doing some calculations with the EM spectrum. So have a go at this one. You kind of know all the equations for this, so try this one yourself. I'll go through it with you in the next couple of slides. So a sprinter runs 100 meters in a time of 10 seconds. Calculate for a radio wave, at how far would it travel in 10 seconds. Okay, so hopefully you remember you're doing your KFC technique. So you would get that the time is 10 seconds, the speed of radio wave, remember, is 3 times 10 to 8 meters per second, and we want a distance. Okay? And if you do this, you'll realize we're using speed as distance over time, plug it in, and we get the distance is 3 times 10. Now that should be a 10 to the 9. It's just when I do my PowerPoint, it seems to mess it up. So it is 3 times 10 to the 9 meters. Hopefully you got that using our KFC technique and your relationship sheets. Let's try a few other ones. Okay, so this one we're looking at satellite calculations. So a satellite beams a microwave signal from the USA to the UK as shown below. Calculate how long it takes a signal to go from the USA to the UK via the satellite. So what that means is that the signal is in America, USA. It goes up into space to the satellite, and then it bounces back down from the satellite to the UK. And we're assuming it's traveling at a straight path of a distance 35 kilometers each way. Pause the video and have a go of it yourself if you're confident. If not, I'll show you the answer in the next slide. Okay, so what we do is, again, our KFC technique. We've got time, speed, and distance. Notice the distance is the sum of the 35 kilometers, which gives us 70,000 meters. Remember, we want distance in meters. We then use speed as distance over time. And then we get our answer is 2.3 times 10 to the minus 4 meters, seconds, sorry, not meters. So just make sure that, again, recognize that this is minus 4 and that this should actually be seconds and not meters. Okay? So hopefully you're able to figure out that answer there. Right, now, final question, which is on our past paper question, and this is just to give you an idea of the type of things you need to know. Okay, so the diagram shows some parts of the electromagnetic spectrum in order of increasing wavelength. So you can see they've been a wee bit sneaky because they've done the diagram in the opposite direction. X-rays, ultraviolet, visible, infrared, microwaves, and they've also missed out some of the actual waves as well. Well, they've missed out the gamma waves and they missed out the radio waves at the end. State a detector of infrared radiation. So straight away they're asking you for a detector. Have a go of that, see if you can think of what the answer is. State which radiation in the electromagnetic spectrum has a wavelength shorter than X-rays. Okay, again, have a wee think about that before we look at the answer. Okay, so first of all, did you get it was the black bulb thermometer? Now notice they do give you a few other things like a photodiode, phototransistor, thermistor, thermocouple, CCD and thermochromic film. You can give these other answers, however, I tend to think it's probably the easiest one to remember, which is the black bulb thermometer. Okay, so that's why I've chosen that as your detector. If you want to choose any of these other ones, you are welcome to do that as yourself. Now, which wavelengths are shorter than X-rays? It is gamma waves, because remember that the wavelength decreases as you go from microwaves to gamma waves. So notice how you had to remember that one so you can see the type of knowledge you need to remember for the EM spectrum. Okay, next question. An electromagnetic wave has a frequency of 1.2 gigahertz. Show that the wavelength of this wave is 0.25 meters. Have a go of this one yourself. It's a show question, so remember you must include this as your final answer. Okay, so hopefully you've tried it and the answer is the following. Speed is frequency times wavelength, or you do your KFC technique, and you'd have to remember it's an electromagnetic wave, so the speed is 3 times 10 to the 8 meters per second. You're given the frequency, so it's simply a case of plugging it in and working out your answer. So notice how we're using the same technique as we did in the previous lesson and also in the worked examples as well. Okay, final part of our question, which is the diagram shows some parts of the electromagnetic spectrum order of increasing wavelength. Identify the part of the spectrum that this wave belongs. Now, the wave it's talking about is the one that we've just done in the previous question, and the wavelength was 0.25 meters. So which part of the spectrum does this wavelength actually belong to? Well, it can't be X-rays because that's times 10 to the minus 10, so it's really on this end of the scale, and in fact, the answer is that it is part of the microwave part of the electromagnetic spectrum. So microwave radiation, and that's that for this lesson.